So let us, good afternoon to all of you once again. Let me welcome you all to the afternoon class of this chapter 7, chapter equilibrium, chemical and ionic equilibrium. Okay. Now in the morning class, I was talking about the characteristics of chemical equilibrium, the characteristics of what you call the physical equilibrium as well. Now, just now, I will continue with this same portion of the chapter and just talk about some what you call irreversible reactions examples, just for the sake of revision. Now on your screen you can see there are some examples of irreversible reactions which proceed in the forward direction only. Okay, I've given few examples, you can have a look at those. Okay, then on the next slide you can see there are some examples of reversible reactions which proceed in both forward and backward directions. Now, as I've told you several times, it is the reversible reactions only which attain a state of chemical equilibrium or ionic equilibrium. Okay, so here on these reversible reactions, we'll be coming across this preparation of manufacture of ammonia, formation of nitric oxide, okay, decomposition of ammonium chloride, okay, uh, formation of sulfur trioxide in the contact process, combination of hydrogen iodide and dissociation of phosphorus pentachloride in this chapter. Okay, so with respect to equilibrium. Now I also explained you what is Lee-Chatley's principle in the morning class. Somebody tell me what is Lee-Chatley's principle? What is Lee-Chatley's principle? I have told you the statement in the morning class. What is Lee-Chatley's principle? What is Lee-Chatley's principle? What does Lee-Chatley's principle state? Lee-Chatley's principle. What does it state? Come on. Anybody? Tell me in a very simple language. What do you mean by Lee-Chatley's principle? What is the statement for the Lee-Chatley's principle? So, let's try to recall. Try to recall. I talked about the Lee-Chatley's principle in the morning class. I was talking about Lee-Chatley's principle in the morning class, and it's so fast that we have forgotten it already. I was talking the Lee-Chatley's principle in the morning class. It's so fast I
That is
forgot.
stress, I think, if I
Yes,
receive
yes. Um,
that product and
yes. So, according to the Lee-Chatley's principle, if you look at the statement for the Lee-Chatley's principle, it states that whenever a system is, whenever a system in equilibrium, whenever a system is in equilibrium, is disturbed, then the equilibrium moves in such a direction which tends to oppose the disturbance. Are you getting it? So this is Lee-Chatley's principle. So on the basis of the Lee-Chatley's principle, the Haber's process has been explained. On the basis of the Lee-Chatley's principle, the contact process has been explained. On the basis of Lee-Chatley's principle, the dissociation of dinitrogen tetroxide has been explained. Okay, so that is Lee-Chatley's principle. Now in this afternoon class, as I've told you, I'll be talking about law of chemical equilibrium and then law of mass action. So I'll be discussing about a detailed mathematical study of the phenomenon of chemical equilibrium, which has been carried out by a very important law, which is known as law of mass action after the law of chemical equilibrium. Now this was, of course, given by Goldberg and Vage in 1864. So now first, without the statement, let me explain you what is law of chemical equilibrium. Now, let us take for an example, a system is in equilibrium, a reaction AA plus BB giving CC plus DT. This small a, small b, small c and small d, these are the stoichiometric coefficients. These are the stoichiometric coefficients, COEFFICIENTS. These are the stoichiometric coefficients. and capital A and B, these are the reactants, and capital C and D, these are the products. These are the products. So let us consider a reaction between capital A and capital B to produce capital C and capital D as the reactants. And we know A, B, C, D, these are the stoichiometric coefficients, which are numbers, whole numbers, 1, 2, 3, 4. Okay. Now, according to the law of chemical equilibrium, the equilibrium constant, that's K which you see over here, this K, it is called equilibrium constant for that reaction. And this symbol in square bracket means concentration of that reactant or product in molarity. So the equilibrium constant is equal to the product, the product, the product of the concentration of the products, the product of the concentration of the products divided by the product of the concentration of the reactants. This is the law of chemical equilibrium. This is the law of chemical equilibrium. And remember, the concentration terms, concentration of C is raised to the power of C, concentration of D is raised to the power of small d, concentration of A is raised to the power of small a, concentration of B is raised to the power of small b. This A, B, C and D, this small alphabet A, B, C and D, these are the stoichiometric coefficients. So if you have any chemical equation, if you have any chemical equation, A plus B is giving C plus D. So for this reaction, the equilibrium constant, of course this has to be a reversible reaction, and this reaction, for this reaction, the value of the Gibbs free energy has to be 0. Then only this system will be in equilibrium. So for such a situation, the equilibrium constant K in terms of concentration becomes like this: Kc is equal to concentration of C into concentration of D divided by concentration of A into concentration of B. This is the law of chemical equilibrium. And please put in your head just now only, the concentration is represented by this bracket, which is a square bracket. Which is what? It is a square bracket. Okay. Now after this slide, moving to the next slide over here, the law of chemical equilibrium. Now we can talk about the definition, the statement. The law of chemical equilibrium states that at a given temperature, a chemical system may reach a state in which a particular ratio of reactant to product concentration has a constant value. That means if I divide the product of the concentration of the products by the concentration product of the concentration of the reactants, that is a constant value. And this constant value is called equilibrium constant. This constant value is called what? It is called equilibrium. It is called equilibrium constant. So this is the statement for the law of chemical equilibrium. After this statement for the law of chemical equilibrium, we move to the next slide to understand further, which is the most important thing in this chapter, which is called as law of mass action. Which is called law of mass action at constant temperature. This law states that the rate the rate at which a substance react is proportional to its active masses, and the rate of chemical reaction is proportional to the product of the active masses of the reacting substances. So that is the law of mass action. Now if you look at the law of mass action from your textbook, it is written like this: at constant temperature, the rate of a chemical reaction is directly proportional to the product of the active masses of the reacting species, with each active mass raised to the power equal to the stoichiometric coefficients. Now, this I will explain you by introducing a slide over here. This statement over here, try to pay some attention over here and try to understand. Now, let us consider, let us consider, I am trying to explain you the law of mass action. Let us consider a reaction between A and B to give what? To give the products. To give the products. I'm writing products for the product. Okay. Now if if I apply, if I apply the law of mass action, so I'll write down over here according to the law of mass, according to the law of mass action, I can say rate of reaction, rate of reaction, it is proportional to the product of the concentration of the reactants. That is concentration of A multiplied by concentration of B. This is according to the what you call law of mass action. Okay, or the same relation I can write it as this way: rate of reaction, rate of reaction will be equal to small k into concentration of A multiplied by concentration of B. Okay, now this k which you see over here, this small k, it is called constant of proportionality. It is called, it is a constant of proportionality, proportionality, and it is better named as, it is named as rate constant. It is better named as rate constant. So try to follow these steps. Consider a reaction between A and B to give the products. If you apply the law of mass action to the above reaction, then we can write rate of the reaction is directly proportional to the product of the concentration of the reactants. Okay, that is K is that is rate is equal to K into concentration of A into concentration of B. Okay, now to get this idea very clear, to make this idea very clear, we can take uh, one more example over here. If I consider another case, say I take another reaction AA plus BB plus small c capital C, giving products, giving products. Okay. Now for this reaction, for this general reaction, if I apply the law of mass action, then the rate of the reaction becomes like this. Rate of reaction will be equal to K. That is the rate constant multiplied by concentration of A raised to the power of A, concentration of B raised to the power of small b, concentration of C raised to the power of small c. Okay. Now this A, B and C, these are called the active masses. What are these called? These are called the active masses of the reactants. Okay. So I think this is clear to all of you. Okay. These are called what? Active masses. Okay. Now the active masses, the term active mass in the statement of the law of mass action, it indicates that the whole mass of the reactant may not be active. That's why the people who are involved in the study of this law of mass action, they introduce this term active masses, assuming that active mass of substance in the solution or gas phase is equal to its molar concentration. That is why whatever is active in the reacting species, that is only taken into consideration. That's why we take it as active masses. Okay. After that, we come to the law of chemical equilibrium, which I've already explained you. Okay. This also I'll explain it once more. Okay. But before that, have a look at the slide. Next one over here. The law of, according to the law of mass action. Okay. The K values Kc, K equilibrium constant. If there is a general reaction like this, then the law of mass action states that the equilibrium condition is expressed by this equation. So this is already clear to you. Okay, very much clear. Then again, I come to the law of mass action over here. The relationship between the chemical equation and the concentration of reactants and products is called the law of mass action. For the general equation, this one, the law of mass action follows this order. Lowercase letters represent the coefficients. Always products over reactants. The products are up, reactants are down. Okay, this is the numerator, this is the denominator. Pure solids and pure liquids are not included over here. Okay, so here we do not include pure solids and pure liquids in the concentration terms of the reactants and the products. Okay. Then, what is actually law of mass action? The law of mass action states that the rate of a reaction is proportional to the product of the concentration of each reactant. Okay, that is what I explained just now. And we can also say that this law can be used to explain the behavior exhibited by solutions which are in dynamic equilibrium. That means which are in equilibrium. That means at any instant of time the reactant is becoming the product, and at any instant of time the product is becoming the reactant. That means the reactant is always becoming the product and the product is always becoming the reactant. This law, the law of mass action, also suggests that the ratio of the reactant concentration and the product concentration is constant at a state of chemical equilibrium. So this is what you are supposed to understand. Now let me introduce a slide over here. Let me introduce one slide over here to explain you properly the law of chemical equilibrium and equilibrium constant. Okay, so here we go. Law of chemical equilibrium and and equilibrium constant. This is important. That's why I am doing it for you. The law of chemical equilibrium and equilibrium constant. This derivation. Try to understand this derivation. Okay. Now let us take a case over here. Okay. A general reaction. Let us say there is a reaction between A plus B reversibly. Okay. To produce C plus D. Okay. Now, in this, let us take that it is an equilibrium. There is an equilibrium between AB and CD. Okay. So, if I apply the law of mass action over here, if I apply, if I apply the law of mass action, then I can write it as a rate. It is a reversible reaction, so there will be a rate of forward reaction. Rate of forward reaction will be equal to, let us say the rate constant for the forward reaction is k1, small k1. It becomes concentration of A into concentration of B. Try to understand this. I'm not using the proportionality sign. I'm directly using the equal to sign and introducing a constant over here k1, which is the rate constant for the forward reaction. Similarly, the rate of reverse reaction, the backward reaction, rate of backward reaction, I can write it as K2 is equal to small k2. That is, this small k2 means the rate constant for the backward reaction into concentration of C into concentration of D. Okay, now as I've already told you, K1 and K2 are the rate constants. This where K1 and K2 are the rate constants for the forward and backward reactions, for the forward and backward reactions. Okay, try to understand this derivation. It's very, very important. Now at equilibrium, we know it is an equilibrium. So at equilibrium, we know rate of forward reaction is equal to rate of backward reaction. This is the main thing under equilibrium. So for this I can equate this equation, this one and this one. I can equate this equation 1 and 2. So I'll write over here K1 into concentration of A into concentration of B, that is equal to K2 divided multiplied by concentration of C into concentration of D. Now if I rearrange this, I will get over here. Let me introduce one more slide over here. If I rearrange this, I will get uh, K K1 by K2 is equal to concentration of C into concentration of D divided by concentration of A into concentration of B. Okay. Now remember that at temperature is constant. It's a particular temperature. So at a particular temperature, at a particular temperature K1 and K2 are constants. These are what? These are constant. They do not change. So therefore, I can say K1 divided by K2 is also a constant. Is also a constant, and this constant is denoted by capital K. And this capital K is now called, it is called equilibrium constant. It is now called equilibrium constant. So this is how we get equilibrium constant. Finally, I can write down capital K is equal to small k1 by small k2 is equal to concentration of C into concentration of D divided by concentration of A into concentration of B. Okay, are you getting it? Are you getting it? So this is how we get the law of chemical equilibrium and equilibrium constant. So if you apply this, if you apply this law of chemical equilibrium to any other general reaction, say there is a general reaction like this, AA plus BB in state of equilibrium with CC plus DD. Then if you apply over here the law of chemical equilibrium and write down the expression for the equilibrium constant, then it becomes like this. Capital K is equal to C raised to the power of small c into capital D raised to the power of small d divided by capital A raised to the power of small a into capital B raised to the power of small b. That is how you get the expression for the law of chemical equilibrium. Okay, so these are known as what? Equilibrium constant expressions. So it is important for you all to remember the definition of equilibrium constant. So which I am going to write it in the next slide. Okay, so the definition for equilibrium constant becomes like this. Equilibrium constant, equilibrium constant, constant K is the ratio, is the ratio of product, is the ratio of product of the active masses, of the active masses of the products, of the products to that of the reactants, to that of the reactants in equilibrium, in equilibrium, in equilibrium with each active mass term, with each active mass term raised raised to the power, raised to the power, which is equal to, raised to the power equal to the stoichiometric coefficient, coefficient. So this is how we defined, this is how we defined the equilibrium constant, which in short, whatever I wrote in the previous slide, K is equal to capital K, equilibrium constant is equal to concentration of the product raised to its stoichiometric coefficient into D raised to its stoichiometric coefficient divided by concentration of the reactants raised to their stoichiometric coefficient, like this. So this is what is meant by and how it is to define the equilibrium constant. Okay, now this was one thing. Now please note that, please note that this equilibrium constant can also be expressed as Kc. It can also be expressed as Kp. Kc means equilibrium constant in terms of concentration, in terms of concentration, in terms of concentration, and Kp means equilibrium constant in terms of partial pressures. In terms of partial pressures. So that is very important for you all to remember. Okay. Am I clear with this? Dear boys, am I clear? So we have discussed how to get the equilibrium constant expressions by using the law of chemical equilibrium and the law of mass action. So here we have applied the law of mass action and finally obtained the law, relation expression for the equilibrium constant expression over here and for a general reaction as well. Okay, so now if you look at the next slide, detailed study of this equilibrium constant is given over there. Whatever I have explained, it is written down over here in quite detail, so that I will not read it out anymore. Now, after this, we move to the next slide over here, where equilibrium constant in terms of concentration is the ratio of concentration of products to the concentration of reactant, each term raised to the power of the Stoichiometric coefficient. It is expressed as Kc. So if you take any general reaction, this is what I've already explained you. After that, what is now important is Kp. For reactions in which all substances that appear in the equilibrium constant expression are gases, if there are gases, if they're not liquid, then what? Then you have to apply pressure. So we sometimes prefer to express the equilibrium constant in terms of partial pressures in atmospheres, Kp, rather than in terms of concentration. So in such a situation, the equilibrium constant in terms of concentration, it gets converted to like this. It gets converted. This is D, small d. This is A, small a. This is B, small b. This gets converted to this expression. Kp, the equilibrium constant in terms of partial pressure is equal to Pc. Pc raised to the power of C, because we know the ideal gas equation Pv is equal to nRT, or I can say P is equal to N by V RT. This N by V, this number of moles by volume, it is called concentration. It is called concentration. So that's why if I introduce this term over here, N by V, what do you call this pressure? This is the pressure, okay, partial pressure. So it becomes N by V RT. So if I, in place of concentration, if I put P, it becomes Pc, partial pressure of C raised to the power of C, small c, into partial pressure of D raised to the power of small d, partial pressure of A raised to the power of small a, and partial pressure of B raised to the power of small b. Okay, so this I will discuss in the next slide, where we have to find the relation between Kp and Kc. Try to understand this very carefully. So this is an important slide on your screen today. So relationship between Kp and Kc. So we know from the ideal gas equation, that Pv is equal to nRT. This ideal gas equation will be discussed in the chapter gaseous state. Okay, the chapter 6. But let me tell you, the ideal gas equation takes the form Pv is equal to nRT, because we have learned in the gas laws P1 V1 by T1 is equal to P2 V2 by T2 in class 10 also, in class 9 also. So using the ideal gas equation, for an ideal gas, Pv is equal to nRT. N stands for number of moles, R is the universal gas constant, and T is the temperature. So applying this, P becomes N by V. This N by V is a concentration. Number of moles by volume gives us the concentration in molarity, and R is a gas constant, T is a temperature. So applying this concept over here, the equation, the equilibrium constant in terms of concentration takes this form, takes this form. And if I replace this Pc by N by VRT, it takes another form, N by VRT to the power of C, N by VRT to the power of D, N by VRT to the power of A, N by VRT to the power of D. So if I take out RT common outside, RT common, the equation becomes Kp is equal to Kc within brackets RT to the power of delta N. Delta N means what? Delta N means number of gaseous product, moles of gaseous product, that is C plus D minus A plus B. Number of gaseous product is C plus D minus A plus B. So this is how we try to derive the relationship between Kp and Kc. So this is important for you all to remember and be able to do it in the examination. Okay. Now, now moving to the next slide, my dear boys. The characteristics of equilibrium constant. This you can read from the book also, but I just like to show you and read out the important characteristics of equilibrium constant. Equilibrium constant is applicable only when concentration of the reactant and products have attained their equilibrium state. Otherwise, no, it will not be applicable. There has to be an equilibrium. That means delta G must be equal to 0. The value of equilibrium constant is independent of initial concentration of the reactant and products. Very important point. The equilibrium constant value does not depend upon the what is the concentration of the initial concentration of the reactants and the products. Equilibrium constant is temperature dependent. It depends on temperature, having one unique value for a particular reaction represented by a balanced equation at a given temperature. So remember, equilibrium constant is temperature dependent. These are the short questions will be asked. It will be asked, is equilibrium constant dependent on temperature? Yes or no? You write yes. Then the equilibrium constant, I am talking about equilibrium constant either Kc or Kp. The equilibrium constant for a reverse reaction is equal to the inverse of the equilibrium constant for the forward reaction. That means if it is for the forward reaction, Kc for the forward reaction is reversed. That means 1 by, this is for the, say, if it is forward reaction, then the equilibrium constant for the backward reaction becomes 1 by Kc for the backward reaction, like this. The equilibrium constant K for a reaction is related to the equilibrium constant of the corresponding reaction whose equation is obtained by multiplying or dividing the equation for the original reaction by a small integer. So this is what they are talking about, the stoichiometric coefficients. Okay, so these are some characteristics of equilibrium constant from which some objective one-word questions can be asked. Okay, now another important thing over here is units of equilibrium constant. Now, what are the units of equilibrium constant? Let us see. The equilibrium constant expression involves the concentration or partial pressure of the reactants and products. The units of equilibrium constant K will depend on the number of moles of reactants and the number of moles of the products. There are two cases to be followed. Case 1. When the total number of moles of product is equal to the total number of moles of reactant, then there is no unit. No, zero unit. No unit. It has no unit. Okay. For example, you can have a look over here. No unit. Okay. but, but, case 2. When the total number of moles of product is different than the total number of moles of the reactant, then Ka will have units. For example, over here, look at this. Nitrogen and hydrogen. 1 plus 3, that is 4, in the reactant. But in the product, it is only 2 moles. So here, the number of moles of the reactant, it is more than the number of moles of the product. So in that situation, the unit of K will be moles per liter to the power of 2, because it will be 4 by 2, okay, divided by moles per liter this way. So we are getting final unit as liter square moles to the power of minus 2. So in such a situation, there will be a unit. Okay, now, so I would like to stop my class here only and continue in the next class tomorrow. Okay, but before that, let me record the attendance. Okay, boys, thank you so much. Have a nice day.
Thank you, sir.